Today's lesson, we're going to look at empirical formulae, molecular formulae, and water of crystallization. We'll also consider the experimental techniques that can be used to find the formulae of metal oxides and water, salts containing water of crystallization. So in terms of a method, you would do this in school, hopefully as a practical, but what you do is you weigh your crucible at the beginning with a metal in it, you heat it under a Bunsen burner. Now you keep the lid on, but you periodically let the air in. You do this because if you do not put the lid on, some of the powder may escape and leave. If you do not open the lid, you will not let in enough oxygen to make sure the metal is fully reacted. You then weigh it again. It should have gained mass as it gained oxygen. However, you don't know the experiment's finished. So what you do is you heat it again and again and again, and keep checking the mass. When the mass is constant and stops changing, that's when you know the experiment's done. So heat until a constant mass is achieved. It's one of the key phrases here. So heat to a constant mass. That's actually quite a famous question in exams. Why do you heat to a constant mass? It's to ensure either you've done the maximum gaining of mass, or in the case of water of crystallization, you've done the maximum loss of mass by losing the water. You will then need to work out the moles of the metal and the oxygen from their masses. So if you subtract the crucible mass as well, you should have checked, you can find exactly how much metal and how much oxygen was gained. Because if you take your metal oxide, so say you started with 3 grams of magnesium, and you turned into 5 grams of magnesium, then 2 grams must be oxygen, the difference between the two. It's a similar principle for water of crystallization. You weigh your hydrated salt, so the salt that has the water is weighed, and you heat it to drive off the water. Once again, you heat it and you keep opening the lid periodically because you have to let it out, but you have to keep a lid so that it doesn't the powder doesn't come out. So then what you do is you heat to a constant mass, so it's no longer decreasing, and you subtract the two to get the mass of water. Then you work out the moles of each of these. I will show you how to do that with an actual question and with an exam question. So let's first look at how to find the hydrated salt. Let's start with that. So 2.5 grams of hydrated copper sulfate, so CuSO4.XH2O, because we don't know how many waters, is heated to give you anhydrous copper sulfate and X amount of waters. You've seen these previously once, perhaps in the reacting mass topic. So now what you do, you find the masses of each. So this is 2.5 hydrated, and then we have 1.6. So the water must be the difference between the two, which would be 0.9. And then what you do is you put these over their MRs to find the moles. Because as you know, the first step in chemistry, if you ever stuck, is to find moles. So the moles of the anhydrous, this one here, would be 1.6 over the MR. So if you add this up, it gives you 159.5. For water, which has an MR of 18, 16 plus 2 times 1, you would do 0.9 over 18. Now, once you get these two numbers, your task is to find the simplest whole number ratio. To do that, we always divide the X by 1, because that's essentially 1 here. So you always divide the water by the other one. In any case, the bigger number over the small number. And you get a ratio of 5:1 in this case, which means that the X must be 5. Then you rewrite the formula of the salt as CuSO4.5H2O. So 5 water molecules within each copper sulfate crystal. And that's how you solve these. I shall show you one more from an actual paper. But first, let's look at empirical molecular formulae. So the term empirical formula means the simplest whole number ratio of atoms in a compound. So for example, if you take butane, which is C4H10, the simplest whole number ratio would be if you divide these by 2. So you get C2H5. So the empirical formula version of butane would be C2H5. Now, molecular formula is the actual number of atoms. So in the case of butane, it is C4H10 because that's what it is. You will learn it in organic chemistry. Sometimes the two formulae can be the same. So like methane is CH4, but because the ratio is 1 to 4, you cannot simplify it any further to make it whole numbers. So that means the empirical and the molecular will be the same. Some more examples would be, I don't know, C8H16. That's a molecular formula. And then C1H2. So CH2 would be the empirical formula version. And that's how it works. Do know the definition if they ask you. Empirical is the simplest whole number ratio. Now let's look at how to actually calculate these. So 1.15 grams of sodium and 0.4 grams of oxygen react. What's the empirical formula? What you do is you make a column. You put the two elements and their masses underneath. Then the first step of chemistry is to find moles. So you divide each one by their AR in this case, because we're looking at atoms, so relative atomic mass. So divide that by 23, divide by 16, and you get the moles. So the first step is moles in chemistry. Once you get the moles, just like the previous question, we need to find the simplest whole number ratio. The rule here is divide by the smallest number. So you look at these two numbers, this one is smaller. You divide both by this smaller number and you get 2. Here you're dividing by itself, so you get 1. So the ratio is 2 to 1. You then put that in, Na2O, and there's your empirical formula. So really, you're dividing twice. Divide by the AR, divide by the smallest number. Sometimes you might get the mass of one element and the mass of the whole compound. So then you need to minus from each other to find the mass of the other element. So for example, if 1.15 grams of sodium reacted and it formed 1.55 of sodium oxide, by taking the difference, you get the mass of the oxygen gained. These examples were with mass, but you're supposed to treat percent as mass. So for example, if they say to you a compound has 40% calcium, treat that as 40 grams essentially. 12% carbon, and the rest is oxygen. You'll need to add these two together and subtract them from 100 to get 48%. Then your first step is moles. So remember, percent is treated as grams, and it adds up to 100 obviously. So divide each one by their AR, and you get the moles. And as you can see, 1 to 1 to 3 is already its simplest form, so you don't even need to divide any further. So the answer will be Ca1C1O3, which is the formula you see here. Now, you have to find the molecular formula. Find the molecular formula from the empirical formula. Someone has to tell you what the actual MR of the compound is. Otherwise, you can't do it. Let me give you an example. And this is the final one on this sheet. A compound has an empirical formula CH2. It has a MR of 28. What is the molecular formula? So once you've worked out the empirical, what you do is you add it up. So 12 plus 2 times 1, and you get 14. Then what you have to do is see how many times this one fits into this one. So 28 divided by 14 is 2. So you can fit 2 of these into this mass. So you double each atom. So it becomes C2H4. And it's done. Similarly, for this question here, if someone said to you that the actual MR of this compound was 300, what would you do? You would do all of the above that you see here. Then you would find what this adds up to. If you do add it, you get 40 plus 12 plus 48, which gives you actually 100. So then you compare 100 and 300, and you'll see that you'll need to times this by 3 to get to the actual molecular formula. So then you would multiply each atom by 3. C8, C3O9. This is completely made up, obviously. It's not a real thing, but that's how it works. In certain situations, you may get that the MR is exactly what the empirical formula adds up to, like in the methane example. In that case, you don't need to do anything. The empirical and molecular are the same. I would recommend showing the examiner that you've done the division there. So in the case of methane, which was CH4, the MR is 16, 12 plus 4 times 1, so you would do 16 over, if they give you an MR of 16, you would do over 1, over 16, so you get 1. So then you can say empirical and molecular formulae are equal. All right. In some scenarios, after you divide by the smallest number, you may not get the perfect situation there. So let me show you what I mean. 1 second. Okay, so I'll just show you here. So if you get, say, a ratio of 1 to 1.5 after you divide it by the smallest number, don't start rounding. You would now need to double it to get 2 to 3. So it basically becomes like maths. You're looking for the whole number ratio. Another example would be like, say you get 1.33 and then 4.667. So this is after you divide it by the smallest number. So then you get this and you're stuck. You think, well, I'm supposed to get some perfect ratio, but I haven't. So what you do not round this down to 1. Think of 0.33 as being 1/3. Now, if you do 1/3 times 3, you'll get 1. So if you times this by 3, you'll get 3.9 recurring. If you times this by 3, think of the 0.66 as 2/3. So if you times 2/3 by 3, you would technically get the whole number again, which is 2. In this case, if you do 4.66 recurring multiplied by 3, you'll actually get 13.99 or something. Now you can round and say the ratio is 4 to 14. Okay, so you're only allowed to round really if you get like a 0.9 or a 0.1. If you get a 0.25, you would times it by 4. If you get 0.33, times it by 3. If you end up with like 1.15, you may have done something wrong, or you may have to think cleverly what you need to multiply it by. But generally, those will be the harder questions. The easier will be just when you do 2 divisions. The harder ones will be that after you've done your second division, so here, second division, so divide by AR, divide by smallest number, and you get 2 nice numbers. If you don't get nice numbers, and you get numbers like these, then you may need to times it. So divide, times. That's pretty much it. I'm now just going to give you one example from a GCSE paper. This is the 2019 one. I'm only going to focus on the calculation part, not this part. So a student heats their hydrated ammonium iron sulfate here. So the water gets driven off. It goes in here and it will cool and condense into water because of the ice bath. So the water is coming off of this crystal. That's the water coming off. So what you do is actually laid out for you in steps. They give you a table. In the first step, they're actually asking you, 1 second. In the first step, calculate the mass produced by heating. All you need to do is minus, if you minus, so the empty tube is this, and this is the mass of the tube after it's been heated. So if you minus these 2 numbers from each other, you would get 6.65. That would be the mass of the anhydrous crystal. Then to find the mass of water, you minus these numbers. You don't care about the test tube because you're looking at how much water was driven off. So that would give you 5.40. Now, that's the first step. Make sure you read the table carefully. Then the rest is actually simple. You look at the MR is actually given to you. So all you do is you find the moles of this one and the moles of this one. Remember, in chemistry, always find the moles. So for this one here, 6.65 over 532, and this one will be 5.4 over 18. You will then get an answer of 0.0125 and an answer of 0.3. Now I told you divide always the bigger one by the smaller one. So you do 0.3 over 0.0125, and you get actually an answer of 24. It may seem big, but that is the correct answer. So that was a end of paper question in the paper one. So I've gone through a lot of examples. If you're confused, there'll be a worksheet attached for you to practice and maybe rewatch the video just to see what's going on. But the bottom line is find your moles and then divide by the smaller number. See you next time. Depending on your syllabus, you may be doing limiting reactants or you may be doing gas volumes. So I'll see you next time.